Okay, so we're going to be going into our sorting workshop. So I will also, I've got a PDF for these slides that I'm going to show you, and I'll put them up when we're done with this. So let's talk a bit about sorting. And really we're talking about sorting, and we're going to talk a little bit about algorithms, and we'll talk about the efficiency of algorithms, something called Big O. So before we do that, here's just an example of something, right? We wanted to go out and figure out how many pebbles were in here. How do you think we could do it? We could actually count every one of them, right? Or we could sort of approximate them by looking at, a square, and we could go in and count how many pebbles are in that square, and then we could figure out how many squares we have, and we could end up, coming up with some kind of answer, right? And we would end up getting what would be an approximation, right? As opposed to an algorithm, which would go through here, and let's say there was some kind of algorithm that could go in and actually find every single pebble that was there, and it wouldn't be an approximation. So when we end up talking about algorithms, we're talking about some sort of step-by-step instructions that gets you an answer. Might take a long time for the algorithm to run. Shouldn't end up wasting time getting you the answer, and it should be correct. It's not any sort of approximation, right? When you end up having an algorithm that you're running, right, the results shouldn't differ with the same input. Now, the sort of drawback to that, I mean, if you think about if you had to think about writing a program to count those pebbles, it would be, you could do it, but it would be a fairly tricky thing to do. So, writing algorithms could be hard, and the other thing is they could be slow. Again, using those pebbles, I mean, maybe it's got to go, there's some program that we have that takes a picture of them, sees there are any shadows here, is there a pebble that could be underneath here, or whatever, that sort of thing. So there is, sometimes you might want to get, sometimes, approximating an answer is fine. So there's a famous algorithm called the traveling salesman problem that basically has a number of data points, and salesman's got to visit all these points and supposed to give the optimal path to solving that algorithm. It's a very, very difficult algorithm to find. I mean, if you have 2 or 3 data points, it's pretty easy. But as the number of data points actually increases, it actually becomes almost impossible to really solve this problem. But again, you can approximate things and get close. But we're not really talking about approximations. We're talking about actually solving these algorithms. And so there's a question of how do we compare different algorithms to say whether or not one ends up working better than the other. Because what we're going to do is we're going to actually do this by looking at different sorting algorithms and determine which of the sorting algorithms that we end up writing is more efficient. So that's kind of the direction where this is going. So there's something called Big O. And with the Big O notation, what we're really looking at doing is we're looking at finding the shape of this algorithm as the number of items in this algorithm ends up increasing. Okay? So when we end up looking at this, we're talking about as our input size ends up increasing, what that does to the time it takes for us to get our results. We're not looking at small sizes, we're looking at big values. So let's say theoretically, right, that we had this algorithm that said, hey, look, based on the number of items you have, n, right, based on the number of items that you have, the amount of time that it takes is going to be n to the third power plus 5n plus 3. With the big O notation, the only thing that would matter here is going to be the n to the 3. The 5n becomes negligible. The 3 becomes negligible. Again, the focus here is on when we're looking at going towards big numbers, and those other values are basically going to drop away to nothing. So what does this all mean? So if this was the shape of our curve, what we're looking at is the shape of that curve over as the value of n gets large. So we're not interested in smaller numbers here. Again, this could be what, let's sort of pretend that this was the approximation of our, f of n curve. We're not at all concerned about the shape of the curve when n is small. We're looking at the shape as n ends up increasing. And so even though we might be able to approximate a curve that's underneath here, big O is looking at the shape of this curve, which is sort of our worst case scenario for these algorithms. And so when we end up comparing these things, it's sort of a pretty coarse comparison to how different algorithms behave. I mean, what it ends up coming down to is that when we end up doing our sorting, okay, we're going to find that the shape of the curve doing one sort of over the other is very different. And again, that's going to make one algorithm much more efficient than another algorithm. So when we end up looking at these algorithms, there's a couple of things to sort of keep in mind. We're not necessarily, if we end up looking at two different algorithms, one might end up being slower than the other. But the thing is, if we end up looking at the algorithms, what we're looking at is really the shape of those curves as the number of items starts to increase, okay? I mean, individually, something in the algorithm might be incredibly slow, okay? But again, it's the shape of the curve that we're looking at. So here's kind of an example of something where, if we wanted to do a console.log, here we could, on the left, we could end up looping over our colors, and we could end up, looping over our colors. And in fact, if colors.value, we could console log I in the value. And you can see on the left, we'd be, running this loop once. As opposed to if you look on the right, and again, this is a bit of a contrived example, but for each of these colors, we're actually looping over 5 times, right? So we're actually looping a lot more on the right than we are on the left. If we were to sort of graph this as n increases, right, you could make the case, well, our algorithm over here on the left is a lot more efficient than our algorithm here on the right, right? We're doing a lot more looping on the right than we are on the left. And this is sort of what this diagram ends up showing, right? Again, for every one of the items that we have, we're looping over it 5 times. But for O of n, we end up dropping this constant, 5. So this is O of n, and this is O of n. So could be that, that doesn't mean necessarily that you wouldn't want to write more efficient code. You would probably want to write the code on the left because it ends up making more sense. But for the sake of argument, for O of n, these have the same O of n, right? Which is basically, that we're, again, they're both O of n. So from that perspective, there's not really a huge difference. What we're really looking at is, when we talk about O of n, is the shape of the curve. And the shape of these two curves is the same. Shape of those curves is a straight line. Now, where things end up really becoming much different is that we could look at that 5n and we could look at that n. And again, the shape is the same, but you can see here that we've got something that's exponential. So the second that you have, if I end up, doubling the number of items that I have, right? If my function basically says the time that it takes is going to be the square of the number of items, it becomes a huge difference. And it becomes a lot slower for these algorithms to run. So when we end up looking at the big O, this would be, even though the function might be 0.5 n squared, right? The 0.5 goes away, and the big O of this other algorithm is going to be n squared, and the big O of whether it's 5n or n is just going to be n. And we'll talk about examples of that would end up being n squared, which you'll end up seeing in the workshop, and examples that would end up being n, and also examples that might also just be 1. Okay, maybe the time doesn't increase no matter how many items you're dealing with. So the common big O notations that we're going to end up running into is that you have this line that's all the way on the bottom that says, hey, look, no matter how much the size is, it doesn't actually increase all that much. Okay, and then we also have the log of n, which is pretty good. If you have an algorithm where it turns out that your curve as your number of input elements increases has a curve that looks like log of n, you're in pretty good shape. I mean, if you look at that, as you go out to these huge numbers, that ends up becoming pretty flat. Okay, n is also pretty good. As the size increases, okay, your algorithm increases with the size. In fact, n log n is also not all that bad in terms of the curve. Where things start to get pretty bad are when you have a curve of n squared, when you have a curve of 2 to the n, and worst case scenario, when you have a curve of n factorial, which is in fact what that traveling salesman problem ends up doing. So just to get an idea of why this becomes problematic, if it turned out that we ended up looking at this input size, and again, we're sort of focused on, we're really looking at the number of operations that it ends up taking us to get a result. So again, assuming that, one operation is 1 nanosecond. When we start looking at this with large numbers, so let's say that we have, we're looking at 1 million items, right? So we're looking at 1 million items, and again, just for simplicity's sake, we'll say that comparing one of the items takes 1 nanosecond. So we're looking at 1 million items. If we look at log n, pretty fast. If we look at n, right, 1 millisecond, it's not that bad. N log n starts to increase a bit, but if you end up looking at n squared, right, all of a sudden, if you ended up having to do that, if that's the curve that you had for your algorithm, we've gone from 19.9 milliseconds, which is manageable, to 16.7 minutes, which someone's not going to wait around if they're on your web page and you go into the database and you're doing some kind of comparison. And if your algorithm is n squared, you're going to be in a whole heap of trouble, right? So you can see, again, looking at the curves, you look at it and, well, maybe it doesn't make all that much of a difference. But again, just sort of going down, and as, again, we're not concerned with an input size of 10, 20, or 30. Although you could see even with n factorial and 20 items, right, that computation is going to take quite a bit of time. So, this is, again, a measurement of how these algorithms end up performing as the number of items increase. So just to get a little bit of an idea of, constant, when the size of the input doesn't really matter, right? If we ended up having an array of values and we wanted to get that value, and we know what the index of the array is, doesn't matter how big the array is, right? If we have the index of the array, we could get it in constant time. It's not going to end up making a difference. As opposed to, let's say that we were, we'll go down to something that's linear. Remember when we were talking about our linked list? We were trying to find something in our linked list, right? We actually have to go through, worst case scenario, we have to go through, and we might get lucky, and the thing that we're looking for is right at the beginning of our linked list, but we might get unlucky, and again, Big O is concerned with the worst case scenario, where the thing that we're looking for is going to be all the way at the end of our linked list. In which case, again, worst case scenario is going to end up being n. You could sort of see if you think about our binary search tree, where we're sort of drilling down to find something, and we could say, hey, look, is it less than this, right? And we've sort of cut our result set in half. All right, is it greater than this? And we go down one more level, okay? With the binary search tree, it's actually going to be log of n. So you could have a lot of items, but you could see based upon the fact that we're really splitting the difference every time that we want to go right or left, it becomes a lot more efficient. N log of n, we're going to end up seeing that's what our merge sort is going to end up doing. That's one of the algorithms that we look at. And again, that's considered pretty good from the perspective of algorithms. We'll find that our bubble sort, which we're going to do, is not going to be nearly as efficient, and there's a huge difference from going to n log n to n squared. I think one of the things that you sort of take away from this is that whenever you're looking at algorithms and you end up seeing that you're doing a looping within another loop, that's where you start to think, wait a second, this could be a little bit problematic if I have a large enough number of items. That's something that sort of jumps out at you, and you go, is there some way that I can make this more efficient? Is there some way to maybe memoize it so that I'm not going into these loops within other loops? And again, the example of the traveling salesman, that's the n factorial one, and that just gets to be crazy. So you have to have some other way of doing those algorithms. Again, that might not give you the exact answer, but it would end up being close enough. So again, this is just another sort of look at how some of these other algorithms work. I mean, you can see that when we have a hash table, we can end up looking up something pretty quickly. And again, our binary search tree is going to be log n. And again, if we look at that binary search tree and we think about again going right or left, we're splitting the difference every time we end up going down to the next level, and that's what ends up making that so much more efficient. So if we end up looking at sorting, it's probably a pretty good example of how we can write an algorithm and understand how efficient it is. So there's a couple of different classic sorting algorithms. The two that we're going to look at are going to be the bubble sort and the merge sort, which out of all of them are probably two of the more simplistic algorithms to look at. So the first one, which is pretty easy to see, is going to be the bubble sort. And so the way that the bubble sort is going to work is that it's going to basically compare two things, and it's going to keep on moving up the chain, right? And basically, again, the sorting algorithm is that we want to have all the lowest numbers to the left, and we want the highest number on the right, lowest number to the left. So you can see that the 6 is moving through here, and what's going to happen here, it's going to compare two items. It's going to flip. It's going to flip. And really, the reason why it's called the bubble sort is that at the end of this, the 8 bubbles up all the way to the top. And then we do it again. And now we start and we do the 5 and the 3. and the 5 starts moving up, and when we're done with this pass, the 7 is going to be all the way at the end. And you can sort of tell that we've got these loops within another loop. We're looping over all the elements. We're basically looping over the number of elements in the set, and for each element, we're bubbling up all the way to the top. So this becomes a little bit of a slow process, right, to get to where we want to go. And you can see we've done this twice. It's not quite n squared, because every time that we end up getting to the top, you know, we're done with this one, and we're done with this one, and by the time we're done with the next one, the 6 is going to be all the way at the top. But from the perspective of approximation, it's close enough to n squared. So that's sort of probably enough of the bubble sort, but trust me, eventually this whole thing will end up getting sorted.
Wouldn't it still be n squared though, because it still has to go and still check 6 and 7 and 7 and 8?
It doesn't have to. Because again, it's starting from the left. If you're starting all the way on the left and you're comparing every other number in front of it, you guarantee that the biggest number is going to be at the end when you're done with that first pass. The biggest number will be at the end, but you haven't taken care of the second biggest number or anything. You're basically just making sure, again, the first pass through, the biggest number is going to be at the end. The second pass through, the second biggest number is going to be the second to last. Again, because you're constantly going and comparing to the next one. So the bubble sort, you're basically looping over the elements, right? You're swapping anything until something is out of order, and you're actually going to come. One way to sort of do this is to, you know, continually do swapping until, in fact, you don't have to do any swapping. So you don't necessarily have to do n squared, but the worst case scenario is if something was in the reverse order, it would actually go through there something close to n squared. I mean, if it turned out, by the way, if it turned out that the whole thing was in order, right? So you're comparing, what it ends up coming down to is that if you ended up going through that loop and you said, hey, look, I just went through this entire loop and nothing ended up changing, you're done. Nothing's ever going to end up changing, right? So that's one way you could sort of short circuit yourself. But we're not interested in the best case scenario for big O, at least. We're interested in the worst case scenario. So this is not the best algorithm, but it will get you to where you want to be. There's a better algorithm, which is called the merge sort. And if we end up looking at the merge sort, what this does is it actually takes all of these items and splits them up. And the theory is that you're going to have a sorted array when you have an array that's a length of 1. And so what it does is it splits these down and it goes to successive sets, and it's going to do the same thing here. So it's breaking them up, and now it's going to end up sorting these sets, and now it's going to focus on these 2 sets. So when it looks at these 2 sets, it knows that the sets are in order, and it can sort of easily go in here and sort the 2 of them. It knows it just has to start off at the beginning here, right? And then it ends up bringing this one. And here, it would be sort of a no-brainer to bring these other 2 down. So this is actually a lot more of a much more efficient algorithm. Again, it just looks at the beginning, compares the 2. Right, here's the 5. And it's got the 6. And at this point, these could totally end up dropping down. So again, you can sort of see it in terms of it being more efficient in the fact that it's sort of splitting the difference. This, similar to the way that a binary tree works, it doesn't quite have the efficiency of a binary tree, which is log n. It's actually, if you end up, there's a way to sort of derive the fact that it's going to end up being n log n. But again, what your goal really is to really go in here and split these up. So if we sort of look at this, what it really ends up doing is splits these down to groups of 1. And it says, and really, once you get to this stage, it says, I've got a bunch of, imagine that you're basically looking at each of these as being a collection of one, right? And at that point, it says, hey, look, each of these collections of one is sorted by definition, right? If you just have one item in the collection, it's sorted because it's the only item in the collection. Now you have, at this point, you can say, hey, look, I've got these two sorted lists. I could compare them, and I've got another sorted list over. Right? I've got these two sorted lists. I compare them, and I've got another sorted list over here, right? So then when it ends up combining these together, it looks at it, says, well, I'm going to bring the 3 down. I'm going to bring the 27 down. I'm going to bring the 38 down, and I'm going to bring the 43 down. And it does the same thing over here. And then, once you get to this stage, again, the reason why it's more efficient is that you're just looking at the front of that queue. You're dealing with the sorted list to start out with. So the merge sort is going to be a lot more of an efficient algorithm. So in essence, you're dividing this array of n elements into n arrays of 1 elements, and you're basically merging the neighboring arrays in sorted order. And in essence, you basically repeat, this process until you're left with one array. Right, so that the idea is, hey, look, if an array is only one element, here's your base case. If your array is only one element, great, you're automatically sorted, right? Otherwise, split the array, and you're going to basically merge sort each half of the array. And in the end, you're going to end up merging the combined halves into a whole. So if we end up looking at the algorithm here, the bubble sort is going to be a lot slower, right? It's that curve, that n squared curve, that exponential curve, as opposed to something that's more logarithmic, that basically not necessarily flattens itself out. But again, the important point is the comparison, and it's going to be a lot faster. There are trade-offs, in algorithms, right, that you have to deal with. Nothing is going to be perfect. One of the things about the bubble sort is that the bubble sort, you're not creating any new arrays. Okay, you're dealing with the same array, and you're basically just moving things around in that array. And I remember we did an example of actually swapping elements in the array where we had to put something in a temporary spot in order to do it. The merge sort is not that bad either, but you do have to create a new array in order to do it. So where the merge sort ends up taking up some space, if that was an issue, the bubble sort is pretty efficient because you're doing everything in line. So the merge sort, in the end, I never saw Harry Potter. I don't really understand it, but it's something. It's some sort of a movie. So really, what ends up happening here is that in the end, and you can sort of visualize this, right? It's the idea that it's a lot faster to sort of deal with sorting lists where you have two lists and they're already sorted. Again, you're just picking things out from the beginning of the list. And in the end, it's the number of steps that it takes to get to that n list of one item. That's really where the log n ends up coming from. I don't know what this part of the slide really is, but this is actually going to take us into our workshop. And so at this point, you could actually, I'm going to pair you folks up, and you could actually start. And really, you're going to, I think within these slides, hopefully I have this in here. There's one other slide that I wanted to give you. I don't know why it's not in this slide, but it was in one of the other ones, if it's not in the workshop, and that is to sort of show you what the algorithm is, at least with the merge sort. That's something that we always had when before when we ended up doing the workshop. So I'll make sure I end up getting you that. For some reason, I didn't see it here in this slide set. So I ended up opening up the workshops. Let me actually stop this broadcast.